during this session, I'd like to talk you through the basic principle of the MUSE data reduction, and I will also give you some details about the two options you have to reduce the MUSE data, mainly the ESOrex and Reflex. And I'd like also highlight pros and cons of the two approaches, such as you can decide whether to go for ESOrex or Reflex according to your needs. Then I will quickly mention some useful information about the user master calibrations that can be retrieved directly from the archive. And then I will jump into the live demo, which consists in show you how to use the interactive exposure alignment available within the Reflex workflow. And then I will finish by giving you some information how to stack together exposures coming from multiple OBs, multiple different OB. But before starting, I'd like to give you some advices. First of all, it is very important that before you start reducing MUSE data for the first time, you need to be familiar with the instrument and with the instrument characteristic. And this can be done either by reading the user manual or the instrument web page. The reason is important is because the observing strategy depends not only on the target characteristic, but also on the instrument characteristic. For instance, in the case of MUSE, we always strongly suggest the observer to break the total exposure time on target on different sub-exposure and to rotate by 90 degrees each exposure, and also to apply a small dithering patterns. And this is because we have found that during the data reduction, this approach provides a much better result in terms of cosmic rejection, but also in terms of having a noise pattern more uniform. Then, of course, you should read the manual, the pipeline manual, and here these are the link to access the pipeline manual when using ESOrex. And here, if you are after details on the algorithm used by each recipe, you need to look at the pipeline manual ESOrex. Then if you want to reduce your data with the Reflex workflow, then you have to read out the manual related to this. And finally, if you have any question or concern during your data reduction, you can always contact the user support department, and this is done by sending an email to usd-help@eso.org, and we'll be happy to assist you. So the entire MUSE data reduction cascade can be consists of two main phases. Let's say stage one consists of 7 calibration recipe plus a more science recipe. In this first stage, what you do, you produce all the master calibration that are subtracted from are used on the science data to remove from the science data the instrument signature. So you will start by running the MUSE bias recipe that allows you to create the master bias. And this recipe also detected the overscan region and trim it. Then there is the MUSE dark recipe. This, however, is not mandatory, it's just optional. If you run it, you will end up having a master dark, but also a hot pixel map. Following the cascade, you will use lamp flat to create the master flat through the MUSE flat recipe. The recipe not only create the master flat, but it also trace the location of each of the 48 slices on onto the CCDs. Then you move the following recipe in order. It should be the creation of the line spread function. However, these two recipes, the MUSE LSF and the MUSE geometry, are very quite time consuming, and because the instrument is stable enough, we always suggest to use the external static calibration. And these external static calibration are basically calibration that are automatically attached by the cal selector to your science data set when you select it from the archive. Just for the record, the MUSE LSF produce the LSF, the line spread function profile, and it computed on each slice separately. And it computed also the dependency on the wavelength. Then the MUSE geometry, it compute the relative location of the 24 slices on the field of view. Then you move onward. There is the creation of a 3D illumination correction. This is done by using the MUSE Twilight recipe that needs to process sky flat. Mind you that the MUSE flat recipe used lamp flat, while the MUSE Twilight used sky flat. And the output is a Twilight cube. As I said, it's a 3D illumination correction. Then you're ready to move to the MUSE Sci Basic, which allows you to remove all the, let's say, all the instrument signature from your science data. Actually, from the object frame, from the standard, and also from the sky, if you do have sky. Whether you have a sky exposure or not, it depends on the characteristic of your target. So if your target is an extended object or a super crowded field, such as the target will fill most of the field of view, and so preventing to use the pixel from the field of view for to measure the sky background, then what the observer needs to do is to go off target and take exposure of the sky in a separate region. So in that case, you will have also, together with object frames, you will also have a sky frame. At the end of this recipe, you ended up with a bunch of pixel table for the object, for the standard, for the sky, and also an astrometry. Then at this point, you're ready to move to the second phase, where you still have 3 calibration recipes, but they are mostly on sky calibration. These are the MUSE standard, and I'm saying on sky calibration because the standard star is observed by the observatory every night that a MUSE is used. To process the standard star, you use the MUSE standard recipe, and this recipe will provide the response curve, which is needed if you want to flux calibrate your data, but also the telluric, the standard telluric file, which is used if you want to correct for the telluric absorption your science. Then if you have a sky exposure, so in case of extended object of very crowded field, then you will have to create from the sky raw frame a so-called master sky. This is done using the MUSE create sky recipe, and the output product is the skylines and a sky continuum. Then there is this MUSE astrometry recipe. The MUSE astrometry recipe is, as in the case for the LSF and the geometry, is very time-consuming, and it again, MUSE has been found to be stable enough, such as we don't need to take this astrometric exposure, astrometric frame very often. So you can use the static calibration that you find in the installation directory. But mind you that it's the astrometric CCS, this static calibration is also contained in the data package you download from the archive. At this point, you can move to let's say to the final one of the final science recipe, which is MUSE SciHost. Now, if you remember, I told you earlier that most of the time the OB consists of multiple exposure. So in principle, you could feed this recipe with all the pixel table obtained from this routine, a pixel table object, a pixel table sky. In principle, you could feed it all together in this recipe, and you could process everything together to obtain a final data cube. But the problem is that the alignment of the different pixel table corresponding to the frame is not so optimal if you run it through this recipe. So what you have to do, you have to run the MUSE SciHost on each exposure, object exposure, and then what you do. In this way, you obtain a pixel table reduced for each object exposure, a data cube, and an image field of view. So you use all the image field of view, all the science exposure. You use it to find a good alignment, and this is done using the MUSE XPalign. Was output is the offset list, where it's a table feeds file containing the relative offset of all the exposure. The offset list, together with the pixel table reduce of all the object exposure, are used by the MUSE combine routine to get the final data cube and also an image field view. So this is really the whole MUSE data reduction cascade. As I anticipate, ESO provide two different options to run to process MUSE data. One is the so-called ESOrex, which is a command line tool. It's very simple. You have to call ESOrex with some option. In this case, I'm just saying that I want all the log to be stored in a file name align.blog. Then I have to give the recipe name and the option. The option are some parameters. If you don't give any option, it means that you are running the recipe with the default value. And then you, very important, you have to give the so-called soft file, which is a list of files with their identification that you are going to process in this recipe. The advantage of using ESOrex is that ESOrex, being a command line tool, it's very versatile. So in this respect, it's very easy to cast ESOrex command into a different script. It doesn't matter whether it's a shell script, a Python, or an IDL, or an R script, it doesn't matter. But the disadvantage is that it does not provide a manual, an automatic data classification. So it means that you have to create your soft file. So you have to tell the recipe each of the file you want to process what kind of frame it is, whether it is an object, whether it is a line list. However, if if you are very new to the MUSE data reduction, so if you never run it before, I would strongly suggest to give a try for the first time to ESOrex, because in doing that, because you have to. The fact that you have to do the data classification by yourself in some sense force you to have you must have a good idea of how the pipeline works. So in some sense you learn a little bit more because you need to know what you're doing. On the other hand, ESOrex, which by this time after all this afternoon talk you should be quite familiar with, it's a GUI-based tool that calls the individual recipe via ESOrex command. So mind you that we have only one MUSE pipeline that can be run either directly with ESOrex or Reflex. So ESOrex and Reflex have just two options to run the same pipeline algorithm. ESOrex has the advantage that provide an automatic data classification through the so-called OCA rules, and it executes all the MUSE recipe in the right order. But the disadvantage in this case is that it's much less versatile than ESOrex. It does have a limited flexibility. I'm not saying that you cannot do different things, but what I'm saying is that you need to change the OCA rules, and this is not trivial. Now, when you select the raw science frame in the archive, then you are directed to a page very similar to this one, where you are asked to select one of these three options. So select just the raw data, or raw science data, or to associate a data set of raw calibration or process calibration. If you use the master calibration, so if you go for the third option, it means that you will get, together with the science data, you will get the master bias, master flat, and so on. So from the point of view of data reduction, these save a lot of time, because as I showed you before, most of the majority of the data reduction cascade consists of calibration recipe. But you also have to be aware that the master calibration that you download from the archive were obtained by using were obtained very well shortly after the science was taken. So it means that they were processed by using different version of the pipeline. So this different version of the pipeline means also different level of accuracy of the pipeline. So as a general guideline, I would suggest that if you're after, for instance, science verification data, you should definitely go for a raw calibration and reprocess the raw calibration with the latest pipeline. But also, if you are reducing, if you want to reduce data not from the science verification, but from regular observing period mode, then it's best to go for raw calibration if the data you are processing were taken within, let's say, the first period since a given mode was offered for the first time. So, and these are the date, the three MUSE mode that were offered. So, for instance, if you're reducing Y-field mode no AO data taken in 2017, then you can easily take the master calibration. Now, let me switch to the demo. So to start with the workflow. you have to call the executable ESOReflex, which usually is installed by the kit, the installing kit in under install and bin. Now, in this case, because in this machine we have many different installation, I'm calling a local installation, and I made an alias that is called MyReflex. So if you type MyReflex -L, you have the list of all the workflow you can run. So if you select MUSE, so you type ESOReflex MUSE, then it will open the general workflow. Otherwise, here, what I have opened actually, is a customized already workflow, MUSE LPO workshop. And this is how it looked like. It's customized because, as you see here, where I have to define the path where my main directory is, I have already the path that I want. So let me just zoom in a little bit more. So as Sabine today told you, you have to select the main directory. In this case, is this LPO workshop, which look like this. In this LPO workshop directory, I do have the data with process calibration. It's a subdirectory containing all the data. Everything that is called m.muse are process file, and muse.timestamps are raw frame. Then you have to tell Reflex where your data are, and in this case my data are under the main directory and data with process calib file. Then let's go to the interesting parameter that define the data reduction strategy for MUSE. Here, let me further zoom in. Here you have to decide whether you want to compute the LSF. As I told you earlier, it's not really needed, so you can leave it false. If you want to change, you double click and then you set it through. Then here, by leaving the default value 0, it means that I want to create a response curve. Although in this particular case, because I'm going to use master calibration, it doesn't really make a difference because I already have a response curve because it's part of the master calibration. And here, by leaving the default value 1, it means that I want to create the telluric and I want to correction and I want to apply the telluric correction. Again, because I'm going to use the master calibration, it doesn't make much difference here. Then here you have to decide whether you want to save or not the data cube containing the sky residual. The default value is false, but you have to set to true if at the end of the entire data reduction cascade, you plan to use MUSE app, which is another workflow, Reflex workflow that allows you to fine-tune the sky subtraction by cleaning further the residual. So if you want to do that, you have to set sky residual to true. Then here you can set the wavelength min and max, consider it, and this can be used. This value means that I'm going to process the entire wavelength range, but if you do have constraint in terms of machine memory, disk space, or if your science is done just in a small portion in a given range of the MUSE wavelength, then you can restrict the lambda min and lambda max to this particular range, a wavelength range, and this will save also time. Then here I suggest to leave the default value, because auto means that Reflex will interpret the best approach. So if it will find the dedicated sky, it will use the sky frame. Otherwise, it will use a pixel from the object frame. And here is, if you have a sky dedicated sky frame, then this is a parameter that define what is the fraction of pixels that are gonna be considered in the sky exposure to calculate the background. In this case, it's 75%, which is a reasonable value. On the other hand, if you're going to create the sky directly from object, so you don't have dedicated sky offset observation, this parameter it's completely ignored, and what's matter is this other second parameter that defined again the fraction of pixel to be considered a sky in the science frame. So in this case, it's the 20%. And then you will have to decide whether you want to run the Raman lines correction. This is applicable only if you're using EO mode, so the Y-field mode, the cloud correction, or the LPO correction provided by the nanofield mode. And this is because this Raman line I do because of the back scattering of the sodium laser, and this Raman line appears, well, you can look in the user manual for to check what is the exact wavelength at which these Raman lines appears, but in general, very close to the region where the notch filter is. The notch filter is the filter that block the emission line due to the laser. Now, if you're not using the EO mode, or even if you're using EO mode, but your lines of interest do not follow on top of the Raman line, I would suggest not to run the correction, because this correction is still, the optimization of this correction is still ongoing. So if you don't care about the Raman line, better not to apply the correction. So at this point, sorry, what you have to do is, let me zoom out a little bit. So what you do at this point, you go here on the data organizer actor, you double click to access to, and here you see that you have association preference. Mind you that this is just, this is a feature that is available just on MUSE workflow. It's not available in any other instrument workflow. Basically, you can tell ESOReflex what type of calibration you want to use. You can use the master calib or raw, or even no calibration at all. So this I'm gonna set the master calibration option, and I click on commit, and that's it. At this point, if you want to see how the if you want to see the progress of the data reduction, then you click on tool, animate, and then where it is. Okay, and then, well, the default value is 0, and you set to 100. At this point, you're ready to go. So I'm gonna start. Mind you that it's gonna be super super fast, because I'm running the workflow in lazy mode. So you see here, it will open the select data set. What I'm gonna show you is two use cases. The first one is how to align 5 different exposure taken with the Y-field mode, These 5 exposures were obtained such as to mosaic a much larger area. And so what I'm going to do, I'm going to ask Reflex to obtain the combined data cube. I'm not going to select the individual exposure because I wanted to run it faster. But you should be aware that even if I don't click here, select the individual, I will still obtain the final data cube relative to each individual exposure. The only difference in between by selecting or not selecting is that the individual data cube will be stored in the temporary directory if you don't enable. If you enable, then the file will be transferred and renamed properly in the Reflex end product. So in this first use case, as I told you, the idea is to map a much larger area, and and I know already because I checked the header that I'm not expecting a lot of overlapping region among the different exposure. And I always, especially when you are reducing data that you did not design, so for instance, data for which you were not the PI, then I strongly suggest you to check the header to try to reconstruct what was the observing strategy adopted. Then I have a second use case. It's a narrow field mode observation of the core of a globular cluster, where 3 exposures were taken with a small offset, and of course the rotation and everything. So I'm gonna start the workflow and see it goes very quickly here because I already have the master calibration, and then also because I'm running in lazy mode. So this is the interactive alignment GUI. If you click here on the image on the list on the left, you can have an idea of the detected source by the recipe in each exposure. You see that I'm changing the exposure, and the color of the detected source change as well. Now, something that you should already notice is that there is a lot of these most likely fake source detected at the very edge, which is usually not a good thing. Then if you click here, all detection uncorrected, you see how according to this specific alignment solution, all the source in the 5 different exposure where the sources are located. And then you just click on the very bottom option, which show you the final alignment. When you see the final alignment, unfortunately, I cannot zoom in. I cannot magnify the entire window, but what you should really do is to check the alignment carefully, and you can do it by enabling the magnify icon, and then you can click on the image. Now, here, for instance, I'm going to check a star that is supposed to be in an overlapping region, and it's it's a fairly bright star. See, but the problem is that even if it's in an overlapping region, I should expect to see 2 centroid, one from one exposure and one from the adjacent exposure, but I just see one. Even if I further zoom in, there is just one. So it's very unlikely that such a bright star was just detected in one exposure, even if it's located in an overlapping region. And then, as I told you, because I know from the header that the overlapping region is not really big, I mean, this solution is not good at all. Another thing that I suggest you to check the quality of the alignment, you can access to this image fit file by clicking File Info. You can double click on Preview Field of View, and then you can open it with the Fits Viewer you have previously defined in the main workflow. And here you can expect better the alignment. But what I've done here, what I usually do, is that I compare this image field of view with the position of stars detected from Gaia. And you can see that in that region, and you can see that basically there is no match. So I'm 100% sure that this alignment is pretty bad. So what I can do, I should first of all get rid of this fake exposure, and the best way, well, the easiest way to do non-exposure, sources. The easiest, quickest way to do would be to change this parameter, B pix distance, that define the number of pixels to ignore starting from the edge. But the problem is that if I do that, of course, I will get rid of all these sources, but because the overlapping region among the exposure is very small, this is not really what I want. I need to detect the sources close to the edge. The problem is that I need to detect good sources. So what I can do, first of all, what I can do, I can change the radio search, the tolerance radio search for the alignment, and this is the R search. Here is a list of different radius that the recipe is using. So first it looks within a radius of 30 arcsec, then 4, and then 2, and then 0.8. Now I know that the overlapping region is very small, so it's smaller than 30 arcsec. So what I'm gonna do is actually remove the first radius, and then the end beans is the number of beans to the histogram. So these end beans should always be twice the first searching radius. So this case is 8. Then what I can do also is to change the maximum number of source that should be detected in each exposure. And by doing that, by default, if I reduce, for instance, this one to, let's say, 30 stars, then of course the recipe will look for the up to 30 sources among the brightest. So hopefully in this way I'm gonna get rid of the sources, the fake sources on the edge, and I'm gonna take the brightest one. So at this point, I rerun the recipe, and okay, and this is the new solution. You see that now the number of sources is much as expected. This is less. Is smaller. I no longer have sources detected along the edge, and this is the new alignment. So if I zoom in at this point, for instance, on these stars, and I zoom further and further in, okay, now you see that these stars was correctly detected in 2 adjacent exposure. These are the two circle mark the centroid of the same stars in the two exposure, and considering that this size is 0.05 pixel, I would say that the new alignment is pretty good. But if you still want further proof, of course, you will have. It's advisable to check also in other overlapping region. But the easiest way here again, you can check how Gaia compares to the new mosaic you just create. So, and this is how it compares. Of course, you see that there is a small shift. But this is sort of expected because, of course, the CC MUSE is not as accurate as the Gaia. So if you need a very accurate astrometry, you should astrometrize a posteriori your mosaic. But the important thing is that if I select, for instance, all the Gaia source and I move, of course, this is not what you want to do, but it's just a check to let you know that if I'm trying to match, for instance, this 4-star here, actually I'm gonna, with the same, more or less the same shift, I'm gonna match also the star across the entire mosaic, which tells me that this alignment is it's much better. It's what I want. So I can proceed. I can continue here to obtain the final data cube that would be this huge mosaic. Then what is doing what is doing now the work, the reflex is actually
so Elena, we have a question from Stavros who asks if because of course the IFU data cube, they are both imaging and spectroscopic data. So what you were showing there with your images, were they displayed at a specific wavelength, or is this the white images?
No, it's the white images.
So it is integrated over the full wavelength.
Yeah, yeah.
Okay, thank you. Sorry for the disturbance.
No, it's fine. So now that the workflow is in the 5th step, the final. So actually it's organizing the output, but hopefully it will start producing, processing the second set of data that, as I told you, is a set of 3 exposure, narrow field mode exposure taken in close to the core of a globular cluster. I don't understand why it takes takes so long. It shouldn't. Okay. Now see here I have this window that tells me that the first data set have been fully processed, and this other window telling me that the second data set is about to be processed. Well, it's in process. So here is the alignment of this is the first exposure with the detected source. This is the second one, and then you have the third. And then if I look at the final alignment, well, at the first look, it might seem a good alignment, but and as a matter of fact, if you look at this is exactly the same exposure, the first alignment. So if you look at, if you have this first a quick look, what you see, I mean, you don't see clearly a bad alignment. What you see, of course, you see a little bit of elongation, but the elongation in some sense is also expected because of the AO correction is done by using an NGS that is in the middle of the field of view. So because of the anisoplanatism, you will expect the correction to degrade very fast when you move far away from the NGS. So what my suggestion is not to let you fool by the first impression. So to go inspecting deeper the observation and the alignment. And for instance, again, here we are gonna zoom in. And as you see, I mean, this is what in one star, this is the centroid of the same star in the three different exposure. And if I further zoom in, see, okay, now this is about 2 pixels, the distance between the blue and the green circle, meaning that it's not such a great alignment. And certainly it is worth trying to improve the result. So now what I can do is, first of all, now I can change, because I have many stars here, I can actually change the B-peaks distance. So I can set, for instance, that the pipeline should not consider the first 25 pixels from the edges. Then what I'm gonna do here again, especially because I'm dealing with the narrow field mode observation, and the narrow field mode has a very high spatial resolution, a spatial resolution of 20 MUSE. So the searching radius of 30 arcsec is absolutely not optimal. Consider that the field of view of the narrow field mode is about 7 arcsec. So 30 arcsec is pretty outside the range. So I will leave 4 arcsec, 2 arcsec, 0.8, and then I will add another one, another searching radius of 1.2 arcsec. And here again, you have to set the n bins twice the first searching radius, and then I rerun the recipe and see what happened. So again, now I see by changing the B-peaks distance, now I no longer have the stars at the edge. The reason this time I wanted to exclude the stars at the edge is not really because they look like a fake detection. They were actually real star. But as I mentioned before, at the edge of the field of view, you expect the stars to be elongated because of the anisoplanism. So it's better not to consider those elongated stars for the correction. So you jump directly to the alignment, and then at this point you can zoom in to check. No, sorry. Okay, sorry. To check the final alignment. Again, I'm gonna look at exactly the same stars as I did before. So I'm gonna zoom in and further in. Now you see that the size of this box now it's half a pixel. So the alignment has been improved a lot. So I can continue the workflow because I'm confident that this new alignment is much better. So and here I already prepared for you the two. You can already see the two alignment. So this is the first run, this is the second run. So as you see, I mean, depending on your target or depending on your observation, you really inspecting the preview field of the preview image of the alignment. It is very important. Now, if you look at these two, at the first look, you don't see a lot of difference, but then if you look more carefully, for instance, here the stars look more rounded, and then if I start blinking the two frame here, okay, if I look, for instance, at this faint star, they are not only more rounded in the second alignment, but because there is a better alignment, I have at the centroid position, I have a higher flux. So so then, okay, because at this point, the two data set has been fully process, and here I have the product explorer window where I can have a look of the various data product that are stored in the different directory. But I believe Sabine already told you about this part. So let's say at this point your data reduction it's finished, it's ended. So because after, of course, the alignment, there is the combination of the data frame and then the creation of the final data cube. Now, before ending this session, I like to give you some tips on how to stack exposure from different OBs. Now, you have to remember that the pipeline stack together pixel table reduced file, not data cube. So if you have, for instance, the final data cube corresponding to many exposure that you want to stack together, you can't do it with the pipeline because you need the pixel reduced table, which are the output of the the MUSE SciPost recipe. So if you want to stack together the exposure from multiple OBs by using ESOrex, well, there is nothing really to say because you have to just follow the entire reduction cascade, and because there is no automatic data organization, it's just you taking care of listing all the exposure in a soft file that you want to process. On the other hand, if you want to use a Reflex, you have to take into account that part of the OCA rules criteria is the object name and instrument mode. Of course, you should not stack together exposure that were obtained by using different mode. By different mode, of course, I mean Y-field mode with another field mode, but even Y-field mode with no AO and AO. It is, of course, you have to keep in the OCA rules this criteria, but if you don't change the OCA rules, it means that if your exposure, all your exposure have different object name, so the keyword in the feeds header ops type name is different, then Reflex will not process all the exposure together. So you have two options. Either you edit this keyword and you set it to the same name, or you change the OCA rules. And to do that, you go back to the workflow. You can double click here on the data organizer actor to open this window, which tells you where the OCA rules sit. Here, you see the path. So what I suggest is to take this MUSE wkf.oca file and you make a copy and you start editing the copy. So what you have to do, you have to go around the lines number 4 on around 500, and then you look for this command. So you have upstart name, you remove it. And then you leave only instrument ins mode, you remove the upstart name. And then a bit further, you also have to strip out these two lines where upstart name appears. And then you save it at this point. Of course, save it with a different name, not in order not to overwrite. And what you do, you upload it again here, the new OCA rules. At this point, you are ready to go. The only thing that you have to do, you have to make sure that all the exposures sit exactly in the same directory, and at that point, everything is exactly the same as I explained before. So with this, I will end the session, and I'm happy to take questions if you have. Hello?
So go ahead if you have a question. Better first raise your hand, or otherwise put it in the chat.
Just for you to know that the question will not be posted online. So for the most shy people, don't worry, just.
Hi.
Hi.
I have a question on the uncertainty estimation from calibration.
Yes.
So do we expect a kind of how this much percentage of calibration error when we do the aperture photometry from the cube data?
Sorry, can you repeat the question, because I'm not sure I fully understood. About the accuracy of what kind of calibration?
Yes, so after the calibration, so when we do the aperture photometry from the science data cubes, do we expect to have uncertainty from calibration errors, like calibration error, so that we can propagate the error to our final flux values?
You mean the flux calibration. So if you extract the in the final data cube, if you extract the spectra, yeah.
Yes, exactly. So do we expect like a 10% calibration error or a 20% calibration error or something like that?
Yeah. Now I understand. Sorry, this is actually a very good question, because it's something that is still under investigation, in the sense that you can have more detail in the user manual, but what has been found is that it sometimes is of the order of 10%-ish, but sometimes can be much higher. To the level of 50%, even 60%. So it depends on what your target is. So for instance, I'm a pretty much stellar person. So I usually deal with stellar field. And so what I do, I always try to recalibrate by using other photometric catalog. But of course, I mean, there is we do take.
I'm an ISM person, so when I do the aperture photometry to get the flux from the image, I can expect, because from aperture photometry I have the error values quite small, so I expect a large error from data reduction. So how do I? So usually I have seen that like 10% or 20% that we assume. but that's quite normal, or how do we?
As I said, the problem is not when you have 10%, you're pretty lucky. But if you want to really assess the error in a very reliable way, you have to compare to a reference catalog, photometric catalog. Okay. So a real photometric, because I understand when you do aperture photometry, but so if you do have another reference photometric catalog obtained with Imager, then you can calibrate the flux over there, and you can also have a much better handling of the error.
Okay, thank you.
You're welcome.
Yeah, I have another question, but I can ask it to someone else. Okay, so that's related to that fake source that we can expect, fake exposure that we can expect in already reduced data, because sometimes we may miss it. We may miss it because if we are looking at a crowded field, so sometimes there can be a fake source that maybe might not have noticed after reduction, right? So in that case, can we check after the already reduced data? Can we check the alignment again, or is there something that we can do using?
Okay, if you use ESOrex, so the command line, of course you don't have the GUI. So what you can do during the data reduction, so you first run the signpost recipe on all separately on all exposure, and that will give you a field of view image. Then you run the alignment, and it will give you the preview, so the preview of the alignment before you actually implement it. And there you can check. But if you don't use the GUI, you cannot really check what is the displacement of the centroid unless you do a proper photometry on the different field of view. But if you download, for instance, a data cube, a reduced data cube from the archive, because I believe, you have seen Martino's presentation, MUSE, it's one of those instruments for which we do put in the archive also the process final data. But there you can only access to the data cube, final data cube, so after the alignment. And if there is something fishy in the alignment, so for instance, you do a PSF profile of few stars and you see that it's not really, sometimes, when there is a displacement in the, a very evident displacement in the alignment, you kind of see a lots of elongation. You might see double stars all over the place. So that is a very bad luck, because it means that you have to download the raw data. And because, as I said, the pipeline handle pixel table, not the final data cube. So the data cube, it's really the final step. And if you want to refine something in the reduction procedure, you need the pixel table. And unfortunately, they are not available in the archive, because if you they are very heavy in terms of gigabyte. So for instance, if you do have a 3 gigabyte data, a final data cube, you easily have a corresponding pixel table that it could be over 10 gigabytes. So, and you have a pixel table per IFU, so it is a lot. So what I suggest to you, you could download the reduced data from the archive, and you look. If you're happy with that, fine. Otherwise, you have to start over from the raw data.
Yeah, raw data. Okay, great. Thank you.
You're welcome.